So in class on last Thursday, we analyzed YY circuits, and today we're going to learn how to make any circuit that isn't a YY circuit look like a YY circuit so that we can analyze it. Okay? So the first thing that we're going to deal with today is transformation between balanced sources. And as it turns out, we actually already know how to do this. So we're going to start with a Y connected source over here on the left-hand side of the page. Like so. And over here on the right-hand side, I am going to have a set of transmission line terminals, and we're going to sort things out here in a moment. So our ultimate goal is to construct a delta connected three-phase voltage source that's based on what our Y connected voltage sources voltages are, okay? So for our delta connected source, we only have access to our transmission line terminals A, B, and C. There is no neutral whatsoever, so we should not have a neutral conductor connection anywhere in our delta connected source. So what is the line voltage that we would see here, VAB, based on our Y connected voltages? So we've done this a couple of times, but I'll go ahead and explicitly write it out again. The voltage VAB is nothing more than the voltage VAN minus the voltage VBN. And so we could express this as VAN times 1 angle 0 minus 1 angle negative 120 degrees, which just looks like VAN times √3 angle 30 degrees. Are we okay with that? Again, we've seen this a couple of times here, right? So now my goal is effectively to force the voltage seen between transmission line terminals A and B for my delta connected circuit to be that. So how am I going to do that? By literally just putting a voltage source there that provides this amount of voltage. So this is going to be VAN √3 angle 30 degrees. Now, what should the voltage be between the B and C transmission line terminals of my Y connected source? So we could do that, but instead, because we're dealing with the B phase here, let's relate it to the B phase of our Y-connected source.
So it'd be just like a normal distance except EVA.
Exactly right. So we could put a voltage here that would be VBN times √3 angle 30 degrees. And lastly, what if I wanted the voltage seen between the C terminal and the A terminal? Actually, put this as VCA, like so. How would I relate that voltage VCA to my Y-connected voltages? A better question is, how is it any different than what we just did? It's literally the exact same thing as what we just did. Yeah, no, that's fair. It's all right to be hesitant about these things, but it is literally that easy. So this would be VCN √3 angle 30 degrees. So we've constructed our delta connected source based on our Y connected voltages. So effectively what we've found is to transform from a Y connected source to a delta connected source, we simply multiply our phase voltages by √3 angle 30 degrees to get the phase voltages of our delta connected source. So here's where things are going to get difficult, and that is complete sarcasm. How do you think we're going to convert from a delta connected source to a Y connected source, which is our ultimate goal? Divide by √3 angle 30 degrees. Absolutely correct. So if we have a delta connected source over here on the left-hand side, where this is VCA, VAB, and VBC, like so. We will divide by √3 angle 30, which is the same thing as multiplying by 1 over √3 angle negative 30 degrees. I'm expressing it like this just so that it's multiplication either direction. There's nothing remotely wrong with just dividing by √3 angle 30. I want to be clear about that. Yeah, it doesn't matter. I just, here. There you go. Nope, just forgot to draw it. Literally doesn't matter at all. So this guy is going to be VAB over √3 angle 30. This will be VBC over √3 angle 30. And this will be VCA over √3 angle 30.
That middle arrow, you need to make it.
For this guy right here, that should be negative 30 degrees, yes. So just to be really clear here, we are dividing by √3 angle positive 30, which is the same as multiplying by 1 over √3 angle negative 30. So transforming from a delta connected source to a Y connected source is pretty darn simple, right? It's just the inverse of the operation that we've actually been doing for a couple of class meetings now. So now let's talk about doing something similar for loads. So let's call this bit transformation between balanced loads. So I'm going to describe the situation that we have. We have a Y-connected load over here on the left, and I'm going to draw this as if all of the impedances were not the same. We're going to come up with a relationship, and then we are going to see how that relationship simplifies under the constraints of a balanced system. Okay. So the reason why I'm doing it this way is because this is a tool that can be used to actually simplify circuit analysis whenever we have an impedance that we can't combine in series or parallel or things like that. Okay. So here I have my Y connected load, and then over here on the right, I'm going to put my delta connected load. So when we're looking at our Y connected load, if we look in between terminals A and B, what is the impedance that we see? Yeah, we're looking in between terminals A and B. Where's the voltage source in this? All I'm expecting you guys to do right here is effectively just resistor combination, except that you've got impedances, so instead of R's, it's Z's. So it's not going to be ZYA and ZYB in parallel. It'll be ZYA and ZYB in series. Just add them up, right? So effectively, what we had, to put things in context here, is something like this, where let's call this R1, let's call this R2, and let's call this R3. We're looking in through this set of terminals where this guy over here is still open circuited, which means that resistance R3 isn't going to contribute anything. So all we have is R1 and R2 in series. The exact same thing, except that we have impedances now, right? So we can see quite easily that the impedance seen between terminals A and B is simply ZYA plus ZYB. The impedance seen between terminals B and C should then just be ZYB plus ZYC. And the impedance seen between terminals C, and A should be ZYC plus ZYA. Anything wild or crazy about any of those relationships? I hope not. Simple series combination of elements. Here's where things are going to get slightly, but not overwhelmingly harder. So if I were to look in between terminals A and B for my delta connected network, what impedance would I see? So I'm going to see Z delta A for sure, but it's going to be in parallel with something because there's other impedances that we have to deal with, right? So I'm going to put a Z delta A up here, which is definitely correct. So let me draw this in a slightly different way, okay? Using resistors, I'm going to erase it in a moment here. So here I have Z delta A. It is directly between A and B. Now, between A and C, so let's put C right here. I have Z delta C. And between B and C, I have Z delta B. So to me, this looks like Z delta A in parallel with the series combination of Z delta B and Z delta C. So I'm just adding these two guys together because that total impedance is between A and B, and it has to be in parallel with any other impedance seen between terminals A and B. So I have Z delta A in parallel with Z delta B plus Z delta C. So that's going to look like Z delta A times Z delta B plus Z delta C all over Z delta A plus Z delta B plus Z delta C. And I can do a similar thing for the impedance that I see between B and C. So that's going to look like Z delta B times Z delta A plus Z delta C all over that exact same denominator, Z delta A plus Z delta B plus Z delta C. And lastly, I'll have ZCA is going to look like Z delta C times Z delta A plus Z delta B all over Z delta A plus Z delta B plus Z delta C. So these are the impedances that I see looking in between the different combinations of transmission line terminals for both my Y connected network and my delta connected network. So if we want these two networks to be equivalent so that we can transform between the two of them, they need to be electrically equivalent. That means that the impedance seen between A and B of the Y-connected network has to be equal to the impedance seen between A and B of the delta-connected network, and so on and so forth. So we would just set these equal to each other, these equal to each other, and these equal to each other, and then kind of see what shakes out. Now, the algebra involved in seeing what shakes out is extraordinarily gross. So I'm not going to make you guys suffer through that. I used to make my electrical engineering students derive this, and they hated it with a passion. So I just got in the habit of just giving it to them, and I'm definitely just going to give it to you guys. Okay. So effectively what we have is a system of equations where we have three equations and three unknowns. And so let me explain what I mean by that specifically, right? It's pretty obvious that we have three equations here because we have this equals this as one equation, this equals this as another equation, this equals this as our third equation. Our unknowns are whichever thing we're trying to transform into. So if we had a y-connected load and we wanted to convert it into a delta-connected load, then z delta A, z delta B, and z delta C are unknown quantities. ZYA, ZYB, and ZYC are known quantities. If we wanted to go in the opposite direction, Z delta A, Z delta B, Z delta C are known, ZYA, ZYB, ZYC are unknown. Either way, it's just a three equation, three unknown system that can be solved. So the results of solving things are as follows. So we're going to call this a delta Y transformation, okay? So this is us converting from a delta connected load to a Y connected load. So the value of the A phase of the Y connected impedance will simply be Z delta A times Z delta C over Z delta A plus Z delta B plus Z delta C. And we can do something similar for ZYB. So that'll be Z delta A, Z delta B over that exact same denominator, Z delta A, Z delta B plus Z delta C. And lastly, ZYC will be Z delta B, Z delta C over Z delta A plus Z delta B plus Z delta C. So this is what our generic set of relationships is going to be. So anytime we have a delta connected impedance, regardless of whether or not it's balanced or imbalanced, we could convert it into a balanced or unbalanced Y connected load. Now let's explicitly constrain things to be balanced, right? So in a balanced system, all of our Z delta A, B, and C have to be the same value, right? So if we looked at our expression for ZYA, that would look like Z delta times Z delta, or Z delta squared. Divided by Z delta plus Z delta plus Z delta, which is just 3Z delta. So this Z delta in the numerator cancels out one of the Z deltas in the in the numerator, and we wind up just getting 1/3 Z delta. So for a balanced three-phase system, to convert a delta connected impedance into a Y connected impedance, we just divide the impedance by 3. That's it.
I understand the, this is like our example, but it's like, it gets more, well, it can't, because it's going too big.
Okay. So now let's talk about going from Y to delta. Not that we would particularly ever have to do it, but it's a useful bit of information. So now we're going to be getting equations for Z delta A, Z delta B, and Z delta C. So this is going to look like, sorry, that Z looks terrible. ZYA times ZYB plus ZYB times ZYC plus ZYC times ZYA all over ZYA. And we're going to have similar relationships for Z delta B and Z delta C. So we should have literally the exact same numerator, ZYA, ZYB, plus ZYB, ZYC, plus ZYC, ZYA, all over ZYB. And ZYA, ZYC, excuse me, that should be a B. ZYB, ZYC, ZYC, ZYA, all over ZYC. So those are our converting from a Y into a delta connected impedance. And now, once again, let's see what comes out when we balance our system. You're 100% correct. So Z delta, we could look at this formally here, right? So we'd have ZY squared plus ZY squared plus ZY squared is going to look like 3 ZY squared all over ZY is just 3ZY, 100% correct. And once again, it's literally just the exact opposite of what we got for the other transformation. All of the things that we're going to be dealing with in this class are going to work that way, right? So we now know how to transform between a delta connected source to a to a Y connected source and a delta connected load to a Y connected load, so that we can make literally any three-phase circuit look like a Y-Y circuit, get information that we need, and then solve for our quantities of interest. So let's put this into practice by working your in-class assignment. For those of you that might have shown up late, it's available online. It's also got paper copies up here. Yeah, it is. I uploaded it. Son of a, all right, maybe I forgot to publish it, but I definitely uploaded it. So let me do that really quick. Should be 8. Yep. Come on, Duo. I didn't put the sheet thingy up yet, turn it in portal. Yeah, it's totally there. Says it's published and everything, so you might need to refresh your page. This is ELET 280, right? Okay. And there we go. All right. So in this first problem, we are told that we have a balanced three-phase delta Y system with a positive phase sequence. We're given our line impedances and our load impedances, and we are also told what our line current is. we're asked to determine the phase voltages at the source. So I want to draw a picture of this system. So we have a delta Y system, which means our source is connected in delta. So here's VCA. Here's VAB. Here is VBC. Now we have our transmission line impedance, ZW. Transmission line impedance, ZW. And transmission line impedance, ZW. We have a Y connected load. And let's just write things down here really quickly. ZW is 0.6 plus J 0.3. ZY is 12 plus J7. We have a line current, which I believe I've been doing in red, so I'll put it right here. IAA. And that'll be 9.6 angle negative 20 degrees amps RMS. And our ultimate goal is to determine the phase voltages at our source, which are literally this voltage, and this voltage. Okay. So I am going to use a single phase equivalent circuit to figure this out. Okay. So my single phase equivalent circuit should look something like this. Here's my voltage VAN. Here's my impedance ZW. Here's my impedance ZY. And then I always short my neutral terminals together because we know that the neutral terminal shouldn't carry any current and shouldn't have any voltage across it in a balanced three-phase system. So we can just replace it with a short circuit. And lastly, in this representation, I'm also going to include my line current IAA. So while our ultimate goal here is to figure out what the voltage VAB, VBC, and VCA is, those voltages will not show up in our single phase equivalent circuit because in our single phase equivalent circuit, we only have access to our our transmission line terminal for that phase and the neutral. We don't have access between the A and the B phase and all of that kind of good stuff. So what we're going to do is we're going to solve for VAN and then transform that from the Y connected source to the delta connected source that we're looking for. And then we'll have our answer. So how would I solve for VAN here?
Current over the
So current over impedance is garbage, just to be clear. Ohm's law is V is equal to I times Z.
Oh, you're right.
Sorry, I mean, I'm not trying to be rude, but Ohm's law is fairly fundamental. Yeah, you should be getting it right. Okay, so using Ohm's law correctly, what would I do?
Your current times ZW plus UI.
Yeah, so my current times those two impedances in series, absolutely right. So VAN would just be IAA times ZW plus ZY. So that's going to look like 9.6 angle negative 20 amps RMS times 12.6 plus J 7.3 ohms, where I just went ahead and lumped them together as a single thing. Now I'm going to throw that into my calculator. I got 139.795 with an angle of 10.086 or 10.08. Let's round correctly, 7 degrees volts RMS. Using that information, how do I get VAB? What did he say? So it shouldn't be dividing because we're going from Y to delta. So we multiply by √3 angle 30 degrees. To go from Y to delta, multiply by √3 angle 30. To go from delta to Y, divide by √3 angle 30. Okay. So VAN √3 angle 30 degrees. So I'm just going to literally multiply my answer by √3 angle 30. And we get 242.131 angle 40.087 degrees. Volts RMS. Yep, and then we would just subtract 120 to get the B phase and subtract 240 to get the C phase. So we don't need to really do any more here. That part's easy. So this was us using our single phase equivalent circuit to determine something that literally doesn't exist on our single phase equivalent circuit because now we know how those transformations work. Okay. So let's look at problem 2. So this time we have a balanced delta connected load that contains a 10 ohm resistor in series with a 20 millihenry inductor in each phase. We have a voltage source that is an ABC phase sequence, 3-phase, 60 hertz, balanced Y with a voltage VAN is 120 angle 30. And we're asked to determine the phase currents in the load, as well as our line currents. Okay, so the first thing that we're dealing with here is we weren't given our impedance, we were given the resistance and the inductance. So we need to convert that into an impedance, right? So Z delta should just be R plus J omega L, right? Because we know that the impedance of a resistor is just the resistor value itself. The impedance of an inductor is just J omega times the inductor value. So that's going to look like 10 plus J. So what's omega going to be based on our problem statement here? 120 pi, right? So 60 hertz times 2 pi is 120 pi. Absolutely correct. So 120 pi times 20 millihenries comes out to be J 7.540. All righty. So now let's draw a picture of what we have. So we're told that we have a balanced delta connected load. So there's our balanced delta connected load. We have a Y connected voltage source. Where we are told that VAN is equal to 120 angle 30 degrees volts RMS. And let's see here. We aren't given any transmission line impedance, so we are just going to make the only assumption that we can, that value is 0. So this is our system. What we are trying to find are the phase currents in our load. Bless you. So that would be this current IAB, this current IBC, and this current ICA, as well as the line currents. So that would be IAA, IBB, and ICC. So there are a couple of different ways that I can think of to accomplish this, but I'm going to stick to using our single phase equivalent circuit because I feel like that's going to be more in line with people's comfort levels, okay? So if I wanted to come up with a single phase equivalent circuit for this system, my Y connected source is still just going to look effectively like our Y connected source. So we're going to have VAN goes here. We have no transmission line impedance. So we put a wire there. I'm going to have an impedance over here. There's my N terminal. And I connect those two guys together. And here is my line current. IAA. So what impedance should go between terminals A and N in my single phase equivalent circuit here? It can't be Z delta because Z delta is connected between transmission line terminal capital A and transmission line terminal capital B. So we have to convert that delta connected load into a Y connected load. How do we do that? Divide it by 3. Absolutely right. So we're just going to have Z delta over 3 here. Okay. So that is our Y connected equivalent of our delta connected load. So how would I solve for my line current IAA? Ohm's law. So VAN divided by Z delta over 3 is going to look like 3 times 120 angle 30 degrees volts RMS divided by 10 plus J 7.540 ohms. So I'm going to throw that in my calculator. And I got 1.591 with an angle of negative 4.421 degrees. Amps RMS. Ooh. Which definitely does not agree. Did I write something here? Let me double check something here really quickly. So 10 plus 1i times 120 pi times 20 times 10 to the minus 3. Okay, so that is x. Did I? Okay, thank you. Let me retype it in. So 3 times 120 angle 30 over. Yeah, 28. Oh, absolutely right. Just mistyped it in my calculator. Thank you for that. 28.745 angle negative 7.016 degrees. Just double checking here. Yep. Okay. Good deal. All right. So we figured out our line current. Now we need to think about how we're going to figure out our phase currents through our load. Okay. So our phase current, IAB, is the current that's flowing from terminal A to terminal B over on the load side of things. So it literally cannot appear anywhere in our single phase equivalent circuit. So we need to figure out how we are going to determine that, okay? So I can think of a couple of different ways, and we will actually discuss both of them, okay? So the way that's probably the easiest to suss out would be, let me put it over here. So I feel pretty strongly that we could figure out what this voltage VAN is. So the voltage drop across our Y connected load. We could transform that into the line voltage, VAB. And then we could divide VAB by Z delta to get our current through that delta connected load. That's one way to do it. So let's work the problem that way, okay? So let me put finding IAB method 1. So what would V capital A capital N be? Same as V lowercase a lowercase n. Absolutely right. There's no transmission line impedance to have a voltage drop over, so our load is just in parallel with our source. So VAN or 120 angle 30 degrees volts RMS. Okay, I'm good with that. What would VAB be? Exactly right. VAN times √3 angle 30 degrees. Which I get to be 207.846 angle 60 degrees volts RMS. And so from here, I can just use Ohm's law and say that IAB is simply VAB over Z delta. Yes, Trylan, I'm gonna help you. Yes. So VAB is the voltage measured between transmission line terminal and transmission line B, which is not the same as the B phase of our building. Yes. So. All right, so we know what VAB is, we know what Z delta is, so I'm just gonna divide that answer by what I have stored in my calculator is X. And I got 16.596 with an angle of 22.984 degrees amps RMS. Let's just double check things here. 16.596, 22.984 seems legit. So that's one method. That's probably the more obvious method. But there is another method that we could use that's actually, I hesitate to call it simpler, but it involves a little bit less math. So I'm just going to put a line over here. And we're going to hit method number 2 now. So for method number 2, what I'm going to do is I'm going to apply Kirchhoff's current law. So I'm going to apply KCL at, actually, let me expand things here. This node right here. Okay. So I have a current of IAA flowing in. I have a current of ICA flowing in. And I have a current of IAB flowing out. Are we all okay with that? So IAB and ICA are phase currents in our load. Because this is a balanced three-phase system, we know that these currents are related to each other. So while it seems like we have one equation and two unknowns, it's really one equation and one unknown because we know that IAB and ICA are related to each other. So I'm going to write this as IAA is equal to IAB minus ICA. Okay. IAB is just IAB times 1 angle 0 degrees. What is ICA in terms of IAB? So if IAB is the A phase, IBC would be the B phase, ICA would be the C phase. So minus 240. Somebody throw that in my in their calculator. Just 1 angle 0 minus one angle negative 240 and tell me what shakes out. You should not be particularly surprised by the result. Oh,
Third.
so root 3 angle negative 30 degrees. So just IAB times root 3 angle negative 30 degrees. So from that, we could say that IAB is just IAA divided by root 3 angle negative 30 degrees. It's negative 30 degrees here because we're going from the C phase to the A phase, whereas it was positive 30 when we were going from the B to the A. Okay, but it's still a very, very similar thing. So we take our current IAA, which was 28.745 angle negative 7.016. Divide that by root 3 angle negative 30, and we get 16.596 with an angle of 22.984 degrees. Amps RMS, I'll be damned, literally the exact same thing, found in a completely different way, right? So you're not beholden to any particular circuit analysis method in these three-phase circuits, just like you're not in any particular circuit analysis in general. You can use whatever makes sense to you, right? So there was nothing remotely wrong with this step-by-step method of finding the voltage drop across the Y-connected load, converting it to look like the voltage drop across the delta-connected load, and then using Ohm's law to find the current. There's nothing remotely wrong with that, but if we know one of these currents, we can just apply Kirchhoff's current law to find the other one. That is just a different way of getting the exact same result. Brock, how may I help you? So for the in-class assignments, I don't particularly care. For the homework, if I ask for all of the line currents and all that kind of stuff, and I explicitly say that the answer given to you includes all three phases, then I want all three phases. Yes. An awful lot of things. So you need to be careful here because we just figured out that when we're dealing with the currents, it's negative 30. But it's all because of the fact that we have a balanced system and everything is separated by 120 degrees is where that relationship is effectively shaking out of. So I want you to notice something here in this alternate thing. We actually just found another transformation. So we figured out how to transform our line currents into our delta phase currents, right? So the reason why I'm bringing this up is because I want to put some things in context here real quick, right? So when we were first looking at things, just setting things up, we saw that in a delta connected source or a delta connected load, the phase voltages and the line voltages were literally the exact same quantity. Just VAB, upper and lowercase, as was necessary depending on which side of things we were on. When we were looking at a Y connected source connected to a Y connected load, we were able to observe that our line currents and our phase currents were the exact same quantities because that current just flowed in series through our transmission line impedance and then our load. So very early on, we worked out what a transformation was between our line voltages and our phase voltages for a Y connected source. We just learned what the transformation is for our line currents to our phase currents for a delta connected something. So it's all really the same thing. It's just, are we dealing with voltages or currents? Lets us know when they're equal, when they're not equal, when to transform, when to not transform. It's all the same damn thing. All right. So let's look at problem 3. And I want to be clear here. This one is going to be difficult, but this is literally as difficult as you could ever make one of these problems. Cannot be harder, and I'll explain what I mean by that here in a moment. So we have a balanced 3-phase system, and our source is Y connected. So let's draw that out. So there's our balanced 3-phase source. We are told that the line voltages at our source, VAB, is 400 angle 45 degrees. So we were given, I'm going to move this B below, this voltage VAB. Okay. Our load consists of 2 balanced impedances connected in parallel, a Y connected load and a delta connected load. So I'll talk about how to draw that in just a moment. And then we are also told that we have an impedance of the line connecting the source to the load. It has some particular impedance. So I'm going to go ahead and put in my transmission line impedance here. Oops, that should definitely be a B. All right, and so now we need to sort out how to connect these loads. Okay. So I'm going to start by connecting my delta connected load. Okay. So for a delta connected load, I should have an impedance between the A and B terminals. So here's a Z delta for that. I should have an impedance between the B and C terminals. And I'm going to give myself plenty of room over here. And here's my impedance connected between the C and A terminals. So are we all okay with this being a delta connected load? Because I've drawn it literally the exact same way I've drawn every other one. So now I need to put a Y connected load in parallel. And so that literally just means it needs to be connected between the same set of terminals for them to be in parallel. So for a Y connected load, I have an impedance connected between A and neutral, B and neutral, and C and neutral. So what I'm going to do is I'm just going to put neutral here. And so between A and neutral is going to look like this. Between B and neutral would be here. And between C and neutral would be here. And so this is what it would look like if I had a Y connected load and a delta connected load connected in parallel. So the reason I'm saying that this is the hardest as it could ever be is because if we had another Y connected load, that would just be directly in parallel with that one Y connection. So we could just lump those guys together. If I had another delta connected load in this system, I could just put it in parallel with a delta connected load and just lump that together to make it look exactly like this. So it literally cannot get harder than this from a circuit analysis perspective. All right, so let's write some things down here. So we know what VAB is. 400 angle 45 degrees, volts RMS. We know what ZY is. That's 10 plus J3. Z delta is 9 plus J6. And then we have our transmission line impedance, that is 0.05 plus J 0.02. Our goal is to find the line currents and the phase currents through each load. So we're just going to worry about the A phase because if we've got that sorted out, everything else shakes out from there easily, right? So here's our line current. IAA. This is our phase current through our Y connected load. So that's IAN. And this is our phase current through our delta connected load, which is just going to be IAB. So this looks gross. I'm not saying it isn't, but we can do literally the exact same crap that we've been doing and sort all of this out in literally just a couple of steps. So this looks wildly intimidating, but because it is a balanced three-phase system, it can't be that bad. Okay? So let's draw our single-phase equivalent circuit. So here's VAN. Here's ZW. Here's ZY. And now I'm going to put in parallel with ZY an impedance. Let me draw this box bigger so I don't run into issues here. Z delta Y. And what that Z delta Y represents is my delta connected impedance transformed into a Y connected impedance so that I can literally just put it in parallel in my single phase equivalent circuit. Okay. So we know what ZW is. We know what ZY is. So let's figure out what Z delta Y is really quickly. So how am I going to do that? Yep, so just Z delta over 3 is going to be, let's see, 9 over 3 is 3, and 6 over 3 is 2. So just 3 plus J2 ohms. Nothing particularly difficult about that, right? We don't have VAN, we were given VAB. So how do we use VAB to get VAN? Which would be dividing by √3 angle 30 degrees. Absolutely correct. So that's just VAB over √3 angle 30 degrees. So 400 angle 45 divided by √3 angle 30 comes out to be 230.940, an angle of 15 degrees, volts RMS. So we now know all of the constituent parts of our single phase equivalent circuit. Now I'm going to draw on our single phase equivalent circuit what we can actually solve for, and then we'll figure out how to solve for whatever's left over. Okay. So our line current, IAA, is definitely something that's going to show up on our single phase equivalent circuit. It always has and it always will, right? We can definitely also find the phase current through our Y connected load. We can't find the phase current through our delta connected load because we don't have access to transmission line terminal B here. So we're going to have to get creative with that. And by that, I mean, we can literally use either of the two methods that we worked in the last problem and wind up getting the correct answer. So let's solve what we can solve for using our single phase equivalent circuit first. So how might I solve for my line current IAA? Let's start there. So VAN just over the equivalent impedance of this thing. Absolutely right, which would just look like ZW plus, I'm just going to say ZY in parallel with Z delta Y. So I'm going to throw that in my calculator really quickly here. So I'm going to have 10 plus 3I times 3 plus 2I divided by 10 plus 3I plus 3 plus 2I. So that's that impedance. I got 85.451 with an angle of negative 14.352 degrees amps RMS. Yeah, it's off a little bit. I probably just fat fingered something in the calculator, but the process. Oh, I forgot the ZW. That's why. So let me try that again. Sorry. X divided by 0.05 plus 0.02 I plus what I have stored in my calculator is Y. There we go. Sorry about that. 83.795 with an angle of negative 14.205. Apologies for my mistake. So there's our current IAA. How might we go about solving for that current IAM? You keep saying it'll be the same, but you're not explaining what you mean by the same. So are you saying that this current IAA and this current IAN are equal to each other? Because I would argue that that be true on account of it splits off. Yeah, so there's that other load thing there that's messing things up. So Ohm's law, okay, what do you mean by that? What do you mean by that? So we did. We did. we found the total current. We're trying to find this part that splits off. So Nick has suggested that we do current division, which I absolutely agree with as one way that we could do it. How comfortable are you all with current division? So since you're uncomfortable with current division, that's exactly what we're going to do. Let's make you comfortable with current division. Okay. So our current IAN is just going to be whatever we have as IAA times 1 over the impedance ZY divided by 1 over ZY plus 1 over Z delta Y. So this might be slightly different than how you guys learned current division in your prior circuits class. I like it in this particular way, just because it can work for an infinite number of elements connected in parallel, not just two, which is the way that it's traditionally taught. Right? So it's exactly like voltage division, except that it's using the reciprocals. Yep, so that's another reason why I like it, is because it looks the same. The way that you guys, and I'm projecting here, Ron, I honestly have no idea how you taught it to them. But usually when it's, let me just write something out here. So you guys might have seen it like this. Where you have to put the branch that you're not finding the current through in the numerator. That confuses the hell out of me. I don't like that at all. So I don't teach it that way and I don't do it that way. Yeah. So if you use the reciprocals, it's the branch you want in the numerator, which makes it exactly like voltage division, except that you're using reciprocals as opposed to. So that's why I like it this particular way. Okay. So we can throw this into our calculator. So that's going to be that answer. Let's store that as Z. So I'm going to have 1 over, let's scroll up here, 10 plus J3. 1 over 10 plus J3 plus 1 over 3 plus 2I. Multiply all of that by what I stored in my calculator a moment ago as Z. And I got 21.692 angle negative 1.552 degrees. Let's just double check and make sure I haven't made an asinine mistake. Doesn't look like I have. That's definitely one way to do it. It is the way that I personally would have done it, because I'm comfortable with that. Another way that you could do it, just for the sake of argument, would be if you found this voltage VAN using Ohm's law, right? So that would just be this current times these two impedances connected in parallel, and then divide that voltage VAN by the Y connected impedance would also give you that current. There's always more than one way to do these things, right? So whatever way you feel comfortable with is perfectly fine by me. So now that we know IAA and IAN, how might we solve for that current up here labeled as IAB? So I don't think it's just going to be a simple division thing here because we have these two loads connected in parallel. That makes the relationships a little bit awkward to deal with, right? But we could, so just for the sake of argument, we could do literally either of the two methods that we did in the previous problem, right? So if we solve for this voltage VAN, which we have a couple of different ways to do, converted it into the voltage VAB, and then divided VAB by the impedance, Z delta, that would give us the current we're looking for. Or we could apply Kirchhoff's current law at this node up here and get it directly in one step. Either way works, and we proved effectively why in the last problem. So it's another situation where it's just whatever you're comfortable with. It's not going to be as simple as just dividing by √3 angle -30. Okay, so let's do that. So how would we solve for the voltage VAN? Okay, so IAA, oops, lowercase a, uppercase A times ZY in parallel with Z delta Y. I'm okay with that. So if my memory serves me correctly about what's stored in my calculator and where, this should look like 226.466 angle 15.147 degrees volts RMS. Just to double check here, 21.692 angle -1.552 times, is that 10 plus J3? Yeah. Comes out to be the same thing. Okay. So all I was doing to double check there is because we know what IAN is and we know what ZY is, we could have just multiplied those two together using Ohm's law as well and got the exact same result. Okay. All right, so I'm satisfied with this VAN. So from here, how do we find VAB? This is where it's appropriate to just do the transformation. So we're positive, absolutely right. Yep. You will. So I get here 392.260 angle 45.147 degrees. And then lastly, how do we find that current IAB? So to be clear, we just found that voltage. So now we just divide it by Z delta using Ohm's law. Nine plus 6I, if memory serves me correctly. And I get 36.264 angle 11.457 degrees amps RMS. Double check. Yep, seems legit. All right. So we found this and this and this, and now we could find the B and C phases of all of those by just subtracting 120 degrees. All right, so that's all I wanted to cover today. So we have 20 minutes left, which means you guys can ask questions if you want to. I want to ask you guys a question. I believe on homework set, whatever's due on Thursday, can't even keep track of it with some of the classes. Did I give you guys 4 problems or 5 problems? 4 problems. Okay, so I'm thinking of giving you guys like 6 problems for this homework set, just so that you have a considerable amount of practice with this analysis. I don't want that to be wildly overwhelming. So it would be due next, what day of the week is today, Tuesday? So it would be due like next Tuesday at midnight, which means you would have the study session or whatever today, if I get it up in time for you to look at it for today. The study session on Thursday, and then the study session on next Tuesday to ask questions about it. So does that seem like an unreasonable amount of work to give you guys practice?
I have a question about what. If we just work out that we can practice. Right, we get one, when we do that work. This question last one was, they all.
Yeah, I mean, this is direct, yes. Uh-huh. Okay, so let's talk very briefly about what we're about to do next. So we've covered circuit analysis, okay? So what we just did is analogous to the circuit analysis that we did at the beginning of the course. After we covered circuit analysis, then we looked at power relationships. That's exactly what we're going to be doing next. We're going to take our ability to analyze these circuits and solve for appropriate voltages and currents and all of that kind of stuff, and then apply those voltages and currents into calculating various power related quantities. So it is 100% just a continuation of what we've been doing. It's just introducing new concepts where we're looking at 3-phase complex power. Just as a huge spoiler alert, if you can calculate the single-phase complex power and multiply it by 3, you've got 3-phase complex power. So it is really a review. It's on the syllabus, whatever. I don't know what day of the week it is, and you expect me to know when a test is.